We investigate the growth of continents and supercontinents from the mechanical point of view. We focus namely on the most recent supercontinent Pangaea that is best preserved and where the processes of continental construction can be depicted. There are two main and contrasting areas. The western interior European part that was formed by amalgamation of Gondwana-derived continental fragments to the northern continental landmass, and the exterior Eastern Asian part where giant oceanic domain was incorporated into the host of supercontinent. This oceanic lithosphere was neither abducted nor subducted, but remained landlocked in between continental blocks. In both cases, the continental growth was consolidated by lower crustal flow of exotic material called relamination.
The Center for Lithospheric Research is a department of the Czech Geological Survey, which is a state research institute. Our main task is to provide expertise in geosciences to the Czech government, but at the same time we are engaged in basic research. Our support to basic research creates an environment where both research and applied expertise can thrive together and enhances our competences. In 2011, the Czech Ministry of Education opened a funding scheme for high-flying Czech researchers with career abroad to establish new research teams within Czech institutions. Karel Schulman, a professor from Strasbourg University, took this opportunity and succeeded. The center concentrates world-class research. In our survey, collaborates with experts from other departments and is also very active on the international scene.
In order to develop conceptual models of continental growth, we start with the fieldwork. It involves outcrop-scale structural analysis on vast regions, accompanied with geological and geophysical mapping. This analysis is completed by microscale investigations, allowing us to determine pressure and temperature conditions, their ages and conditions of deformation. In that way, we can construct the dynamic and kinematic model for the given portions of the lithosphere. These models are finally tested by geophysics, in particular potential field methods and numerical and analog modeling.
To determine pressure temperature conditions and age of mineral fabric, it is important to select a suitable sample already in the field. We observe crystallization deformation relations under optical microscope. We measure mineral compositions on electron microprobe. Based on a holo composition, we calculate the thermodynamic model, which is a map of equilibrium mineral assemblages. Then we trace a pressure temperature path based on earlier fabric observations. The age we calculate from radiogenic isotopes on radiogenic minerals, and such pressure temperature deformation time path of a rock then serves towards building a large-scale geodynamic model.
Mineral fabric represents the arrangement of minerals in a rock on a microscopic scale. And properties such as grain size, crystallographic preferred orientation, grain distribution, they all in a way reflect the mechanical properties, or rather mechanical state of a rock during deformation. And since the mineral fabric is very closely related to metamorphic conditions and geometry of deformation, it is extremely important to quantify and understand these properties in order to create and test reliable geodynamic scenarios or models.
Gravity and magnetic data provide information about the density and magnetic susceptibility contrasts related to the juxtaposition of different rocks, as it is the case in orogens. The main objective of potential field analysis is to enhance the location and trend of these contrasts by applying suitable filtering procedures. Then, by correlating the gravity and magnetic signatures with geological and tectonic information, we can infer the significant crustal structures, including their continuity in depth. In both Europe and Asia Paleozoic orogenic belts, the gravity data analysis and modeling contributed to assess the occurrence of rocks which originated elsewhere and then were later tectonically emplaced into their current position. In the Bohemian Massif, the 3D forward gravity modeling established a felsic Ordovician continental relaminant underneath a Devonian magmatic arc and back arc basin. In southern Mongolia, the 2D forward gravity modeling showed the existence of a Cambrian magmatic arc relaminant underneath a Devonian oceanic domain.
We study relamination using numerical models. The models were developed in collaboration with ETH Zurich. There they have vast experience with the modeling of subduction and collision. In order to obtain relamination in such a model, we need to incorporate all relevant physics, which means that, for example, we need to have different kinds of materials in the model to mimic the behavior of the crust and mantle and their buoyancy. Besides that, we need to take into account melting and weakening by melt. The difficult task is to find a model that can explain data from natural origins and that is at the same time simple enough we can understand its dynamics.
Analog modeling is exciting because you can observe development of orogenic scale structures in front of your eyes within minutes or hours. We are interested in the mechanical role of the relamination process on exhumation of the weak, partially molten lower crust in accretionary or collisional orogens. This type of modeling is done in cooperation with the Institute of Geophysics of the Academy of Sciences of Czech Republic. In this model, you can observe formation of large-scale folds cored by partially molten material that resembles development of metamorphic domes in the Central Asian orogenic belt.
Our main objective is to understand geodynamic evolution of accretionary systems developed between Tethesian interior and Pacific exterior oceanic plates along eastern margin of supercontinent Pangaea. Here, relamination and accretion processes formed specific continental oceanic hybrid lithosphere that was later incorporated into the heart of Pangaea supercontinent. The thermomechanical aspects, the timescales and length scales of the formation and transformation of these lithospheric segments into the major continent are the main questions of modern geodynamics. The Center of Lithospheric Research and its research partners home and abroad wishes to engage this problem in future.